So what we're doing here is equilibrium, okay? So this is kind of an important topic. It's two-dimensional equilibrium. You'll run into this a fair amount, as you go through engineering school. In 2D equilibrium, you got three equations you can use. Sum of fx is 0, sum of fy is 0, and sum of moments about any point, anywhere, would be 0. The idea is the object is in balance, okay? And we're just going through some examples of this. We did touch on the fact that the signs of the things you put into equations indicate the direction you assume they act. The signs you get out of equations indicate whether or not your original assumptions were correct or not. Okay? So the first step is always to draw a decent free body diagram. Assume whether your forces are positive or negative on a certain line. You do want to get the proper angle when you put the forces on the object, and then you go ahead and solve for them using these equations. Okay. So that was the first one we did there on page 400. And what we did kind of an analysis there of the most efficient way to approach a problem too. So we looked at that, okay? So really I like to keep with one equation and one unknown. And we've just kind of worked through some things. We're kind of using things we've learned before, like how to take a moment and how to resolve a force into components. And then on this problem here, we were looking at breaking distributed load down into discrete forces that we can then analyze. So we did this problem here. This involved distributed loads and couples. Right? So we did a couple of these problems with beams and things. Now I did have some homework with this. So do y'all want to, what should we do? Want to have a look at some of this homework? Yeah. Why don't we do that? There's just two of them, but they're both a little bit, they've got their aspects to them. They're a little complicated, so let's have a look. So 264 looks something like that. What you've got is a cantilever. We have a distributed load on that. All right. So what we want is a free body diagram of this. This is problem 264.
I think ours is 262. Ours is 262 for some reason.
Thank you. Yeah, you're right. Yeah. Thanks. So 262. This has been renumbered. There we go. So 262. All right, so when I see something like that, here's what goes through my mind. I'm seeing a trapezoidal load. Okay, I need to break that down. So that's one of the first things I think about. So I'm going to turn that into a rectangle and a triangle, right? Now I notice this height over here, 800. So that means the height of my rectangle is 800, right? Now, if the height of the rectangle is 800, what does that leave for the triangle? What do we got there? I think 1800, okay? We good with that? So what you're going to want to do is break down those two shapes, the rectangle underneath and the triangle up above. All right, so to break those things down, what you want to do is to find the areas of them, because when you have the areas of the figures, what you then have is the load. Right? So the initial thing I do on a problem like this is I'm going to break that down. So I'm going to take 800 newtons per meter, and I'm going to multiply it by the distance over which it acts, and that's 3 meters. And that comes out to be 2,400 newtons. And that'll be down, of course, because that's a weight. And then we're going to say, well, where does that act? And where that acts is in the middle of the rectangle, and the middle of the rectangle is half of 3. So that's going to be at 1.5 meters from point A. And what I'm doing there, I'm taking 3 over 2, and I'm getting 1.5 meters. Okay. So do we have any questions on that?
What did you say about 3 over 2?
Well, the total width of the beam is 3 meters. And the centroid of a rectangle is in the middle. So I would take half of 3.
Okay. I was just wondering.
Okay. And so that's putting me right about here. And I'm going to have a load of 2,400 newtons right there. And that will be a distance of 1.5 meters here. Okay. Now I'm also going to have to figure out the triangle, so you can go ahead and do that. Okay, the triangular load will be about there, I think. And you're probably shooting for about 2,700 newtons, I think, on that. But run the numbers, make sure that I didn't make an error there, but there we are, 2,700 newtons. So we got any questions on that first bit there? Okay. All right, now when I'm doing these, I just think of these as processes of just kind of breaking things down. So what I have here is this beam. I'm going to have 2 loads on it. I'll probably put them underneath just to stay out of the way to the cable. And I've got the cable. So I want to come up with a Freebody diagram of this thing. So I've got 2,700, and make sure that I got that right, and 2,400 newtons. Okay, and then the distances for those are 1.5 meters. And you can figure out this distance here. Okay. You also have the force in the cable, which is given. And the force in the cable is 3,000 newtons. All right, now we need reactions. That's what we want to find. So for reactions, we're going to have RAY, RAX, and then this is a cantilever. Okay, generally speaking, now this turnbuckle, this cable kind of confuses things a little bit, but normally a loaded beam is going to try and rotate clockwise in this case. So what we're looking at are the reactions, how we counteract that. So that would be something like that, MRA, coming back the other direction. Okay. So that's kind of the breakdown of that. It's a little bit like doing a resultant. You're trying to take those loads and simplify them is what you're trying to do. All right. Then the rest of the problem just involves calculating everything. Okay. So you're going to go sum of fx and set that equal to 0. And run that. You're going to go sum of fy and set that equal to 0. And run that, and then you're going to sum moments. Normally on these cantilevers, I sum moments about the point where the reaction is. So this would be about point A, and that will equal 0. And what are we going to have there? We're going to have MRA, right? Now I've drawn that counterclockwise, so that'll be positive. And then I've got minus 2,400 newtons times 1.5 meters. And then I'm going to have minus 2,700 newtons times whatever that moment arm is there. And then I'm going to have to deal with that 3,000, aren't I? Like so. And that will allow me to solve for MRA, I think. Okay. And that should be 5,479 Newton meters when you run the numbers. Okay, RAY ought to be 3692. And that'll be newtons. And RAX ought to be whatever, 2649. So what we want to do is break these things down and try and simplify them as best we can.
Can you go over why the moment goes down?
All right, so the question there is why does the moment go, from our perspective, down, which I guess would be counterclockwise, as opposed to clockwise, which would be up. Okay, now the first thing I would say is I'm not sure on this one. I'm guessing. And if I get it wrong, I'll just get a negative answer. So I'm not concerned worrying about whether I choose the proper direction. It's not going to cause me any problem if I don't, because I'll just get a negative answer. And that negative answer means I picked wrong, so I've got to turn it around. That's all a negative answer means. Now, the reason I think it's going counterclockwise is I have this loaded beam. I do have two forces down, one up. They're all roughly in the same, they're all roughly equal. And so I've got more force down than I've got up. So that's going to take that beam and try and turn it like that. So if I embed this beam into the concrete here, into this wall, that wall is going to have to torque it back the other way to counteract that. Because we're looking at reactions, how the beam reacts to the loads that are applied. Is that all right? Okay. Yes.
So I guess if you're looking for MO, it would be the other way.
If you're looking for a resultant.
Yeah.
Yeah, right.
Okay.
A resultant would be the other direction. And those are they're related things, but they're different. They're act in opposite ways. You can almost think of the reactions as opposing the resultant in a way, opposing it. Okay. Other questions? Okay, we good? All right, we got another one. And what is this, 260, what is this, 263 maybe? 263. This is a similar kind of thing. Now, what you want to do on this is you want to break that 900 Newton per meter load down and multiply it by the distance over which it acts. You're going to get a force like that on account of that load. You are going to want to find a moment arm for that, okay? So you're going to want to get the moment arm to that load. Okay? Now, we want to look at those symbols. Those are like schematic symbols, and they mean things. What I've got is I've got a triangle with a dot on it over there. And what does a triangle and a dot on it stand for? That is a pin joint, right? And when I see a pin joint, I don't overthink this stuff. When I see a pin joint, I do that. I put two forces at right angles. R-A-Y, R-A-X. That's all there is to it, okay? And then at C, I see a narrow rectangle with two dots on it. And looking back, I think it's page 260, is that right? I've got kind of a diagram of all these. That's a linkage, all right? What that does is either push or pull on the line between the dots. So that'll go like that, and that'll be RC, okay? A linkage pushes along the line between the two pins on the linkage. So that will be 72 degrees. So the thing I want to emphasize about making these free body diagrams, again, is don't overthink it. Just look at the connection, put the forces that the connection represents. That's it, okay? Do your deeper thinking later when you solve the problem, okay? So that's kind of the free body diagram right there. You need to account for this couple right here, which is 2,000 Newton meters. And then we've got 900 newtons. No, we got 2,700 or something like that up here. Okay, so you're going to want to find that force and that moment arm. And then you just proceed to try and solve this thing. Now, the way you solve it is, you know, you've got three unknowns, Rex, Ray, and Rc. You're going to try and take the unknowns one at a time. Now, a very good strategy that comes up when you have a pin joint is a pin joint, by its definition, has two unknowns acting at it, Rax and Ray. So it's always a good idea, if you see one of those, you can rarely go wrong, let's put it that way, by taking a moment about it. Because when you sum moments about A, you've already eliminated two of the unknowns because they act right through the pin joint. So if you take sum of MA and set that equal to 0, you will solve for RC. Okay? So if you do that, you need to include the couple. Do you include the moment arm with a couple? You don't, okay? You just put that couple down there in that blank space I've created because the moment arm is already there, right there. It already has the moment arm attached to it. You don't need to include any sort of, even though, and that one doesn't even have a moment arm. But that's a couple coming off of a motor. That's going to twist that platform, okay? So that will just go in there as a couple. Okay, you're going to have that blue force there, that's negative, force and moment arm. And then you're going to have a little bit of a trig going on there for that RC. And then you're going to have a moment arm on that. Okay. Are we all right with that? Yes, question?
Do you want us to find the resultant force of that, or do you want us to break it into X and Y and then add it?
When you say it, of that, or I'm not quite sure, of the RC, you mean?
Yeah, of RC, sorry.
I often just do the breaking down part in the equation. I'll just put the trig in there to get the Y component.
Yeah.
Does that answer your question? Yeah, I usually do that in the equation. You could do it previously if you wished. I don't really care. I tend to do it one way, but it's not that way's right. That's how I do it. All right, and when you do that, you're going to get RC. Okay, and RC is 2086. All right, now once I have that, what I like to do, or I use moment equations usually as the first one. That's the normal pattern. But moment equations are more complex than force equations. So the next thing I would probably do is run force equations because they're simpler. They take less time. I'm less prone to make error, et cetera, et cetera. So if I can go with force equations, I just go ahead and do that. So I'd go sum of Fx and set that equal to 0, and sum of Fy and set that equal to 0. And when I did that, I can come up with these forces. Rex is 645, and you're going to have to do that. So Rex is 645 newtons. And run that, and you're going to get Ray was 1316 newtons when you do the force equations. Okay. So that would be the approach to that. And you're kind of going through a series of steps. You're first breaking down those forces into simpler forms. It's kind of a resultant kind of thing that you're doing there. You're not really doing a full resultant, but you're breaking each individual force down. And you're representing those supports as forces. Okay. Once you do that, then you run an equilibrium equation, usually starting with a sum of moments equal to 0, about a point that has two unknowns, and then a sum of Fx and a sum of Fy is a fairly common pattern on this. All right. Yeah, question there.
For the Freebody diagram, are we accounting for the 600 newtons of the weight of the platform too? Just at,
thank you. Yeah,
just at like a random, like our considered center.
Yeah, okay, my bad. Yeah, that should be there. So let's get that in there too.
My question, would it would just be on the entire beam itself, not proportional to where the 900 newtons, or like where you find that force coming.
Right, because the platform extends that full 4-meter length is the deal. So you want to include that. Now where you put that 600 Newton force is you put it at the center of gravity of the platform, unless you're told to do something different, which, you know, or I guess I would say in the middle of the platform, because the assumption would be that the platform has uniform density. So yeah, I neglected to put that in there, so let's get that in there. That would go right there. And that would be 600 newtons. And we're going to have a little trouble sneaking that in there, but we'll put it here. Now, which way, what's the sign on that one going to be? Is that comes down to the right of A on the moment equation. What do we got on that? We'll just kind of sneak that down there. So as that thing pushes down to the right of A, which way would it rotate? What's that now? So, I think what we would do, any doubts? Go like that, push on it. Now we're putting in, we're showing what this does, okay? We're calculating the reaction, but we're not writing the reaction here. We're putting what it does. Okay? So as I push on that, what's going to happen? It's going to go clockwise. Is that good? So that's going to get a negative, all right? So you need to include that, and thanks for bringing that up. There we go. All right.
So that moment about the 2,000 newton meters, that's just about that pin joint only?
Yeah, the moment is applied at the pin joint because there's a motor at the pin joint doing that. So it's at A, but it is included just as a couple into the equation, all right? It'll just go there. And the way I think about that is it already has a moment arm in it. It's a Newton meter, so you don't, the fact it's right at A doesn't, you still account for it. It's still a moment that you apply in the moment equation. Yeah, question?
I noticed this force only applied from B to D, so that if I'm finding that distance that the 600 newtons is applied, so I probably want the distance from the center. Not the middle between B and D, but the distance from, I don't want the number, I just want to make sure it's concept.
Yeah, okay, let's clean this up a bit because we kind of ended up putting more stuff on there than I thought we would, but we got RAY and RAX. We don't know those. So this will be a little cleaner free body diagram. So there's RAY and there is RAX. That's on account of the pin joint. Here is RC, which is angled at that angle shown, 72 degrees. Now we have the 600 Newton weight, which is associated with the platform. That goes in the middle of the platform. Okay. This platform is supporting this load up above it, which is a separate force. 900. Yes. So that's 600 Newtons. That will be in the middle of the 4-meter platform.
But I should also assume that 900 newton meters is affecting the platform from the middle of the platform? Or
no, from the middle of the 900 Newton distributed load. Okay. So because a distributed load goes in the centroid of the load.
Okay, cool.
We good with that? You got any? Any questions on that? So there's a free body diagram that we're dealing with right there, a little cleaner version. And then the standard approach again, moment about the pin joint, that will get you RC. Okay, so sum of MA equals 0 to get RC. Sum of FX equals 0 to get RAX. And then sum of Fy equals 0 to get RAY. That's kind of the process that you work through to get to those reactions. Okay. So are we all right with that? Okay. Okay. So that stuff's due Friday there. All right. All right, why don't we look a little bit more at these moments here these equilibrium problems. And then we'll, let's just spend a little bit more time with those, okay? So let's just have a look at this one and then see what we can do to expand on this a bit. All right, so we're on page 420 is where we're at, okay? All right, so let's have a look. So what we did here, we have a little bracket, okay? We've got a pin joint at the top of the bracket. So we're on page 420. And as we always do with these things, we want to turn it into a free body diagram. This is what we worked through on Monday. So we took the pin joint at the top, we turned that into REX and REY. We have the 40 pounds there over on the left, like so. We have the 20-pound weight of the bracket, and then we have the reaction, okay, coming up on the roller at B. Now the ramp is 30 degrees, so we get that, 60 degrees, so we take 90 minus the 60, and that's where that 30-degree angle comes from for the reactive force at B. Okay. So there's our free body diagram. Now this is kind of a little bit more in full 2 dimensions than the things we've been doing previously. Okay. So we're doing all right here? Okay. All right. So let's have a look here. Now the first thing we want to do is come up with a strategy to solve this. And the strategy involves finding one equation with one unknown. And now this is equilibrium. So we've got different equations we can use. Some of fx, some of fy, and some of moments. Now what we want to do here is to take moments about a point, okay, where loads are applied, where unknown loads are applied. That's normally what you do so that you can then solve for the other unknown forces. So if we look at those 4 equations that we could use, some of fx, some of fy, and some of moments, let's kind of have a look here and see how many unknowns we would get from those equations. Okay. And we went through this on Monday. So in the x direction, we've got Rx, but also Rb. So let's have 2 unknowns for force equation. And the y, we've got Rey and Rb also. Rb's angled, so it's got x and y components, so that's 2 unknowns. If we take a moment here about B, we will have Rx and Ray as unknowns. Okay. So those first 3 options get us 2 unknowns in each equation. That's not a good way to start. So the place to start is to take a moment about a place where there are 2 unknowns acting, and that would be the pin joint right there. Okay? That's going to get you 1 unknown. Now you see the note on there that I would point out. There's a difference here between the pin joint, which has 2 unknown forces, Rex and Ray, versus the roller, which has an angled unknown. Now the angled unknown has 2 components, but they're both components of Rb. So that's really only 1 unknown at B. So when we take a moment about A, we're going to just have that one unknown to solve, okay? That's the strategy. That's what we're thinking about when we work through those. So taking a moment about a pin joint is a good way to start. Okay, so we good with that? All right, then we took a moment about A. All right, now when we do that, we just account for each of the forces acting there. We've got the 40 pounds to the left, we've got the 20 pounds in the middle, and we have RB. Those are the forces to account for. So when we sum moments about A, we just account for those things. So what we're doing is combining forces with moment arms. Okay. So 40 pounds, that's a Y force right there. Or excuse me, an X force. Y moment arm of 8 inches. 20 pounds, 1.5 inch moment arm. We've got cosine 30 RB, which gets you an X component with a Y moment arm of 8 inches, and sine 30 RB, which is a Y component of force with an X moment arm of 6 inches. Okay. Combine all those together, we got RB. So the first equation is usually the hardest because it's a moment equation. Okay. Once we got that, we can come back with the simpler ones, the sum of fx and sum of fy, to solve. Okay. So we doing all right with that? We got any questions? We went over that a bit on Monday. Okay. All right, let's kind of look at another one here. Let's go, just take this one step further. And this is kind of an important concept I want to get to. This is on 430 is where this is at. So this is another bracket. It's like the one we just did. It's got one little complicating factor here, though, and we have an angled portion from the bracket that goes from B to C. So there's a certain approach I want to take on these things, okay? And there's a way I want to be thinking about this, okay? Now, first off is we always do, let's get a little bit of a free body diagram going on that. So why don't you take that and convert that into a free body diagram. Just take a minute and see if you can do that. Again, don't overthink it. Just look at the connections, the reactions, and put forces there that represent the motions those reactions would prevent. Any questions? Just ask somebody or ask me. I'll be walking around.
So there's just going to be a normal force perpendicular. So on, it's kind of the same thing on C. Is it the same thing?
Identify the flat surface.
Yeah.
To the flat surface.
Okay.
Show the angle in there.
Okay.
Okay, so we want to get a free body diagram. And what we got up there at A, what is that? That's a pin joint. So we get forces that are at right angles to one another, right? Now, I don't care which way I got RAX going, or even RAY. I care that they're vertical and horizontal, but if you drew them down and to the left, there would be no problem with that, okay? They have to be at right angles, and I would probably draw those in the x and y directions, but I wouldn't get too worried about which direction you show, because when you solve the problem, the equations you solve will prove out which way they act, okay? Okay, we've got a roller on a ramp at C, so the force is perpendicular to the ramp, like so. What's the angle of the force? We got a 20-degree ramp. So what's the angle of the force?
70.
It's, 90 minus the 20, okay? So that would be 70. Okay, so that's where we start. That's a free body diagram of that bracket, okay? So we got any questions on that? Should we go all right?
The weight of the item.
If the weight of the item of the bracket is not given, and generally the rule on this, and this is more of a rule in a textbook than it is out when you're working, but if they don't give you the weight, you assume it's kind of minimal, it's negligible, okay? So if it's not given, you can pretty much ignore it, would be the idea. All right, now we got a free body diagram. That's always a good start. All right, now the next thing we want to look at is how are we going to solve this? What is equation number 1? Okay. Whoops. There we go. What's equation number 1? How are you going to start that? About A, because it's a pin joint, there's 2 unknowns there. If I take a moment about A, I can solve for what's going on at C, can't I? I can get RC if that's the case. Okay. Now, you want to anticipate that. You want to say, I'm going to take a moment about A, because if you anticipate that, what you then want to do is if you want to connect all the points where the forces are applied, and that would be B right here, and C, you want to connect those to A with X and Y dimensions. That's what you want to do. So what I would suggest doing on this type of problem, and this is a fairly common 2-dimensional problem, is working through that and using some trigonometry and breaking down anything that is angled into an X and Y component. That will make coming up with the moment equations much more straightforward. So what you want to do is, once you've decided that you're going to take moments about A, is create a set of dimensions that connect each of the applied forces and reactions to A. That's what you want to do. So what you have then is an angled bracket from B to C. So my goal here is I'm going to take moments about A. I want to connect these points to A with X and Y dimensions. So my goal here is to get that angled armature and break it down into X and Y components, like so. Okay. So how about doing that? Get that angled arm there. You have the dimension down below, 8 centimeters from B to C. You should be able to figure out the angle. So get those 2 sides figured out. Just take a minute there and see if you can knock those out. The angle you're given up there is 120 degrees. Okay, so you've got a 120-degree angle up there. With that, you should be able to have enough information to be able to, as they say, trig out the line from B to C and get that broken up. My goal here is to come up with a nice set of dimensions from A to each of those sources. If I have a nice set of dimensions there, I can just knock a moment out. But I want to get the dimensions first and then do the moment. That's my intent here, to get that worked out. Okay. So we're just doing some right angle trig here, I think. And we got an 8 centimeter angled line. All right, what's that angle down there in the vertex of that triangle, pray tell? Right here? About 30, eh? Okay. We're good with that? So 90 minus the 120 gets the 30. And then it's a right triangle and a little bit of trigonometry there to get that broken up, right? All right. So we good with that? We're doing all right. So I'm getting 0.4 and 0.693. Yeah, I went off into meters. I often like to get moments in meters, Newton meters. So that's 0.0693 meters and 0.04 meters. Okay. There we go. We're doing all right with that? Now, the reason I'm doing this is, or why I would suggest doing it, is once you have your free body diagram here, of course, I want to generate moments. Now, the way we've done moments, and a common way to do it, is you take the force, break it into x and y components, and then multiply it by x and y moment arms, okay? I want to get those x and y moment arms lined out and ready to go. I don't want to have to kind of think about an equation and then moment arms at the same time. I want to get all the moment arms lined out, good to go, then I'll generate the equation. What I've noticed is I have trouble kind of going back and forth between the two. I'm more apt to make error. So what I'd like to do here is get all those moment arms lined out, okay? And the other thing I want to emphasize to you is you're going to run into a fair number of problems like this down the road. And they're going to be all different sorts of things. They're going to be brackets, and they're going to be fixtures on engines, and they're going to be prosthetic limbs, and they're going to be sports equipment. They're going to be Lord knows what they're going to put in those problems in the book. It doesn't matter, okay, what the objects are. What matters is creating a set of dimensions. Figure out where you take a moment from, make that essentially the origin of your coordinate system, and then create x and y dimensions to the points where the loads are applied, okay? Get beyond the picture in the book. We're just analyzing the forces and how they act, okay? So regardless of the picture, break everything down into x and y components and create a dimension sketch. That's what we want to do, okay? So we good with that?
So are you saying there's a moment about A on this picture?
These forces will cause a moment about A, yes. When I combine them with moment arms, they will, yeah.
In the positive direction, and the reaction will be negative?
Well, as I have the reaction, that's a complicated question. I think the 48 newtons there will cause, what will be the sign? Why don't you come up with a moment? Let's do a moment about A. Let's go ahead and do that. Set that equal to 0. Just put the moment caused by that 48 newtons. What is it about A? Why don't you just start with that in your moment of about A equation. The positive and negative gets a little bit complicated to answer your question because it depends which component you're looking at. Sometimes a force can have two components. One component will cause a negative moment, the other one positive, and I can't just answer your question quite so simply. Okay. Why don't we just start with the 48 and get that in there. So we're doing all right with that 48 newtons? All right, what do we got? I'm not sure what the number is.
48 cosine 43 times 0.03.
Yeah, all right, what we've got there, we've got a 43-degree angle right there. We want the x component, right? Now, if we look at that in a little bit more detail, if you look at that 48 newtons, what's going on with that? That has two components, right? X and Y. Which one will cause a moment? The X. Will the Y cause a moment about A? Not so much. Okay, so we're after the X component. We good with that? We got any questions on that? Okay.
This negative sign.
Yeah, that's right. That's going to be a negative.
Clockwise, you probably wanna call it all negative, right?
Well, let's see. So here's how I would build that. I would start with the force. Okay, now I want the X component. I've got a 43-degree angle in there. So that's 43 degrees. I want the adjacent side, so that will be a cosine of 43. And then, so that gets me the X component of the force. I will combine that with a Y component of moment arm, which would be 0.03 meters, that's 3 centimeters. Then when I've got the numbers written down, I look at the sign, okay? Now, if I pull on this bar here, if I pull on it that way, that bar is going to come around that way, is that correct? It's going to come around clockwise. So when I see that, I go, okay, that's a negative. That's my thinking on that. Force, component, moment arm, sign. I don't put the signs until the end. I put all the components in there, all the numbers as positive, and I put the sign in at the end, okay? All right. How about this 70 degree force and RC? What are we going to do with that? If we're good with that force? Okay, so let's get the two components for the 70 degree angle reaction. So let's get that going.
Is it gonna be times 48 newtons also?
I'm sorry now?
Or was it gonna be times 48 newtons also?
No, that's a force there. We don't know what it is. So it's just RC.
Exactly.
Force, you're going to want a trig component and a moment arm, and you're going to want to do that twice. Okay? So let's get that done twice. So the RC will have two pieces to it. One will be an X, the other will be a Y. And let's try and get the proper moment arms with that. Okay? So we got RC right there. And then we just went through the moment arms. So there we go. That might be the, I'm sorry about the size of that. It's just not working in this room so well, but there we go. So that's a 0.04 and a 0.0693. We've got the RC at 70 degrees.
Do I do 0.04 plus 0.03?
Yeah, I think you do, because we're taking moments about A is what we're doing. Okay? So we got sum of moments about A. There we go.
Is the first one supposed to be negative?
Yeah, I'll let you put the signs in there. What we want to generate there is an X and a Y component of RC, right? So cosine 70 and sine 70, are we all right with that? What I've got there is a right triangle. I'm using this 70-degree angle. The unknown force is the hypotenuse. Okay. Now, when you want the signs on these components, it's, I always make this as visual as I can. So go ahead and draw in those two components, if that will help you. And I think in this one, it might be a good idea, all right? So I'm going to draw in the y component. That would be up. And the x component would be that way. Okay, there are the two forces. So look at those and figure out how each of those independently would rotate that bracket. Okay? And that will tell you what sort of signs to put in there. All right. So that cosine 70 RC is the x component. Okay, so which moment arm would I use with that? For the x component there. Yeah, now I got an x force. If you think of pushing on a wrench on that line, the wrench would be connected like that, right? Y direction. So an x force goes with a y direction. All right, and that is 0.07, is it? I think, meters. Now, what's the sign on that when you push on the wrench to the right and your wrench goes up to the nut up there? It's gonna, yeah, it's coming around counterclockwise, so that's a positive. Good with that? Okay. Now, keep in mind that the component of force is an x, the moment arm is a y, okay? They're different always. If the component of force is a y, as we see here, the moment arm will be an x, all right? So we doing all right with that? I think it would, yeah, because what you're doing is you're coming up and around like that. And again, any sort of tricks, if you have doubts about this, there's lots of little tricks to use. Push on your paper, draw an arrow that circles around the point, whatever works for you is fine. Okay, now I've already got that moment arm in there. That's 0.0693 meters, okay? And you can kind of see all these different things you have to think about at one time to do these problems. That's why I want to get those dimensions just lined out. I don't want one extra thing to think about. I'm going to make less errors if I get a nice clean dimension sketch. Okay? And then I'm going to be able to just fill this in. Okay, now that's counterclockwise, so I think we know the sign on there, right? That's a positive. We're good with that? So we good with that? We got any questions? There we go, a little smaller version. That's it. Okay. So that's kind of an important problem here because this is something we're going to encounter a lot. So there's steps. I think about it as a process. Freebody diagram first. Figure out where you're going to take moments about next and dimension in the x and y directions from that point to the forces. Then generate a moment equation. And then hopefully after that, after we've done that hard moment equation, we get 11.8 newtons up and to the right for RC. How would we finish this thing off? Yeah, we got RAY, RAX, and keep that simple. See, don't go more moment equations unless you have to. They're more complex. So force equations to finish it up, okay? That'd be the way to go. Okay, so sum of fx, sum of fy will get you rax and ray. Like so. I'll tell you what, why don't you do sum of fx just for fun? Let's knock that one out. let's just start those off. Sum of fx equals 0 equals, and then you just put the stuff that it equals in there. You'll have to use a little bit of trigonometry there again. A couple of those forces will require that.
Yeah, sorry. I thought you meant like.
Well, I got RAS plus 11.8 newtons cosine 70, right?
It's the
Yeah.
force,
And then just normal to this one.
Minus
That force
cosine
must come up
43
right.
times 48.
90 minus 30.
Yeah.
Oh, you went to the right? Or negative left? It's just cosine of 43.
I'm getting 31.1. We getting to that all right? Something like that. All right.
So we can
You know, I think it was a good guess. And it's, again, it's fine to assume that. And it turned out to be a positive answer, so. Did you assume the value? Yeah, right, no problem. Just trying to-
But how would that be?
Because the answer is yes. If there's a negative answer, it's turn it around.
It's by itself. RX is just RAX.
Well,
Because it's
the negative sine 43,
So,
48
just separate.
that's coming straight down at
Yeah, you just
the corner there, right?
at the corner.
Is the 43 newtons, there's like a, is that like a cable there? kind of
Right,
thing, or-
yeah, there's some sort of force.
Some sort of force there.
Yeah.
So doesn't that pull perpendicular to the y-axis? So how do we know if it's gonna rotate the thing at all?
I mean, I wouldn't assume those are perpendicular. Or what do you say, I can't quite
Since it's coming straight down, what's to say that the y component, the sine 43 of the 48 newtons, what's to say that that's gonna rotate the object at all, because that's going straight down?
It doesn't.
It doesn't.
It was the cosine 43 that rotates down.
So if we're gonna call the RAY a sum of sine 43, 48, wouldn't that 43, 48 just go to 0?
No, because forces and moments are in different things, they're doing different things.
Okay.
This is like, you know, if you have a wrench, you know, you don't push right on the bolt, right? Because that doesn't cause a moment.
So its moment would be 0, but its force is
Yes,
still.
yeah, they're separate categories, they're analyzed
Okay.
separately, yeah. Other questions? All right. All right, so that's a pretty good work through on that one. That's a typical problem, and you know, as I say, if you thumb through a statics book, you're going to see lots of different situations. You know, lots of different pictures and diagrams, but it breaks down to this, okay? And so get beyond the picture, so to speak, and turn it into something like this. That's how you approach these things. And there's a kind of a sequence to it that you want to work through. Okay? And the dimensioning, I think, is important. You know, I think that you're kind of analyzing some of these things a little differently sometimes. So what I like to do is compartmentalize it. You know, I can work through trading in dimensions. I can do that. Then I can move on to the next step. When I start trying to mix everything together in one big step, I just make more errors. So I think it's a good idea to get the dimensions first. Do we have any questions on that?
We're all gonna start laughing.
Good deal. All right, let's do some of these for Monday. So how about 271 and 272 and 273? And those will be due Monday. Now, one thing on this,
We'll have class Monday.
that's a good point. So they'll be due Wednesday.
No, school, Monday.
And that will be the 19th. Thank you. Okay, now have a look at your book. Remember how you gave some of you replacement problems on that 3D moment? If you have a newer edition of the book, if you have, well, let me word it differently. If you have fall 2019 or earlier, you need a handout, okay? And I have them. If you have a newer edition of the book, which would be fall 2019B or winter 2020, you don't need a handout, okay? So if you need a handout, I've got them. I've got replacement problems for those three here in my hand, okay? Same thing online. These are posted for those of you online in Moodle, the replacement problems. So use the newer problems. And look at the your book to determine which one you have. All right. All right, and again, for those of you online, just to check to make sure you got the right problems, here's 271 ought to look like that. Here's problem 272. It ought to look like that. All right, and then there's problem 273. So if you don't have that, they're available on in Moodle, okay? So if you have an older version of the packet and don't have these versions of those particular problems, you can download these versions from Moodle, okay? And I'll make note of that on the assignment posting.